Hello, everyone. We are now halfway through, almost halfway through the semester seminars. And we are very happy to have Professor Lara Dolecek give a talk today. He is a professor at UCLA. And before that, she was, I believe, a postdoc at MIT. And before that, she was a graduate student at UC Berkeley. At about the same time, or I believe with significant overlap with our Professor Servate there. And much before that, actually, she was in my high school. It's mine, right? But we were there at different times, right, for obvious reasons. And she is currently a distinguished lecturer of Information Theory Society, IEEE. And she has gotten many awards, NSF Career, and many other paper awards, teaching awards, etc. And some are with her students. And it may be that for this topic, the students got a poster award.
Yeah.
Paper, right. So that's very nice. So without further ado, if you'd like to share the screen, Lara.
Yes, let me do that. All right, can you guys see my screen?
Yes, very good. Right,
full screen. Full screen, great. Thank you very much, Amina. First of all, thank you for the invitation to give a talk in your seminar. I had the pleasure of speaking with the colleagues at Rutgers this morning, and it was nice to see all of you, even if it's virtual. And as Amina said already, this work is actually spearheaded by my students who had received a Best Poster Award at the North American Information Theory, School of Information Theory just a few months ago. So the subject of our presentation today will be dealing with how to overcome data availability attacks in blockchain systems. So as you know, blockchain systems are in the news. Bitcoin stock is through the roof, and I'm sure many of you are playing that. You play that game as well. And so we, in this work, we're trying to identify some interesting problems in this domain. And what has emerged, at least from our point of view, is to take the view of the observe some of these problems through the lens of coding theory, and more specifically, graph theoretic constructions. So today I will talk about data availability attacks in blockchain systems, and we will see what kind of role channel coding can play in these types of issues. This is joint work with my very talented graduate students, Deborah Navmitra and Lev Taz, and all three of us are with the EC department at UCLA. Okay, so let's continue. All right, so this is the overview of the presentation for today. First, I will briefly introduce the overall setup, and we will then identify two key problems that we are interested in studying further. The first problem deals with the data availability attacks on light nodes. So here I'm using a lot of notation and terminology that may not mean a whole lot right now, but hopefully when we introduce the problem, it will become clear what we are talking about. And the second problem will deal with data availability attack, again, data availability attack inside blockchains. In the end, I will summarize the presentation, tell you where we're at, and what are the other things that we are working on here. Okay, so let's get started with background and central problems. Again, blockchains is something that many of you are familiar with, at least in general setting. This is an example of a distributed ledger, and this allows for decentralized trust platforms without a centralized entity. Many applications have now been identified in finance and currency, and these are just one of a plethora of examples of cryptocurrencies for which blockchains is, of course, the prime technology. But now there's many other emerging applications that are using blockchain type architectures, for example, in healthcare services, industrial IoT, supply chain management, among others. And so let's now take a closer look at the two problems that we're going to present in greater detail today. So our first problem is the issue of prohibitive storage overhead. So here, because there is no centralization, this ledger of transactions is maintained by a network of nodes, in the sense that every node in the network maintains the exact very big copy of the entire ledger forever. And so, as you can immediately imagine, there is a significant storage overhead as a result. And we pulled the numbers just a few days ago. The ledger size in Bitcoin and related systems is already in hundreds of gigabytes. And of course, it's bound to grow even bigger than that. So this, of course, becomes a limitation for resource limited nodes who then therefore cannot participate in this type of system. So one solution that has been proposed early on was to introduce so-called light nodes. And this is how light nodes operate. They only store block headers, so it's a much smaller fraction of the storage requirement than what a full node would have to do. They can verify transactions included in a block, but they cannot verify transaction correctness. And they need to rely on honest full node to let them know that something has gone wrong, which is fraud notification. The second problem is, again, issue of scaling. So in terms of throughput and latency, Bitcoin and Ethereum, for example, have very poor numbers, really. We are talking about a throughput of only a few transactions per second, and it then takes even longer to confirm the correctness of the transaction. Ethereum is slightly better by nature of how things are recorded, but this is nowhere near to some other, say, financial transactions that we so leisurely utilize. Like Visa processes more than 10,000 transactions per 1 second. So these are orders of magnitude differences. And so the solution, therefore, is to run side blockchains to improve on these throughput and latency results, so that the more side blockchains we have, the more parallel computations we can execute. And then in this case, side blockchains push their hash commitment of their block to the trusted blockchain, which serves as know-it-all. And the order of transactions will be the same as the hash order in the trusted blockchain. And then trusted blockchain would only store, this is one proposed architecture, would only store the hash of the side blockchains. And then since they can, side blockchains can make commitments in parallel, things can be done much faster. So this leads to higher transaction throughput. Now, there is a problem with these alternative architectures. As you can imagine, they solve one problem, but they may introduce a different type of problem. And one problem that has been has received a lot of attention is the issue of data availability. This issue is known as data availability attack and can be described as follows. So again, light nodes, which we introduced to remove some of the burden of storage, since they store the header, only the header of each block, trusted blockchain only stores the hash commitment of the side blockchains. They are both vulnerable to data availability attacks, which I will describe next. So light nodes are subject to data availability attacks when there is a majority of dishonest full nodes in this trusted blockchain. So those are the ones that have now colored in red in this blue block. Trusted blockchain with side blockchains is subject to data availability attack when there is a dishonest majority in this one of the side blockchains. Again, these are now marked in red. And the way this data availability attack would occur is that an adversary creates an invalid block. So this is true irrespective of whether the attack is on the light nodes or on the trusted blockchain. So a header generates an invalid block. It has a header which is marked in green. This header is the hash commitment that gets sent, but it has this piece of block that it hides. So this is this invalid transaction.
Lara.
So yes.
So I think maybe I missed, what is a side blockchain?
So side blockchains are introduced as an alternative architecture to improve the throughput and latency in the baseline architectures. So you can view them as running their business in parallel and only pushing hashes to the trusted chain.
Okay, thank you.
Thank you for the question. So now we are talking about the data availability attack. So how does this attack happen? So adversary generates an invalid block, and by hiding the invalid transactions, which are some subset of this invalid block, which is this stripe in red here, it can actually trick light nodes to accept this invalid header. And the adversarial side blockchain, going back to Predrag's question, can commit an invalid hash to trusted blockchain. So these are two separate problems, but they all stem from this description of the data availability attack. So now I'm going to describe in detail how does this data availability attack on light nodes come about, and what can we do to remedy it. So systems with light nodes in a dishonest majority of full nodes are vulnerable to these so-called data availability attacks. This has been recognized in previous work. So we are now looking at the subset of that architecture where we only have full nodes and light nodes. So adversary is the one that's going to send this, it's an adversary, so it creates an invalid block in the sense that it hides a portion of this block that it sends to the full node. And it's going to send a header to the light node. The light node by definition only receives the header because it's constrained in terms of storage. So honest nodes, they can see that something is missing, but they have no way of verifying these missing transactions. So they cannot create what is known as no fraud proof. They know something is missing, they just don't know what it is. Light nodes themselves, because they are limited in their capabilities, they themselves cannot generate these so-called no fraud proof, and they will simply go on and accept the header. And so how would then a light node that has accepted this header marked in green test for whether this header truly corresponds to a legitimate block? So one solution is that the light node will say, well, is this block available? But we already said that light node cannot store a full block. So what can it do at best is therefore it can sample or request some random chunks of the block and hope for the best. But adversary at the same time can hide a small portion. Let's see how this works. So suppose you have a block, and let's say we partition this block in 16 chunks, and the adversary hides this small portion. So 1 out of 16 chunks is hidden. On the other hand, this light node randomly requests, say, 2 chunks. These 2 green chunks are requested. And what is then the probability of failure? Probability of failure is then that the probability that a light node accepts this block as being valid, i.e. accepts the header, but adversary has a hidden chunk. So probability is really that it had not requested this hidden chunk. So this is now probability of failure with 2 random samples, which can be viewed as sampling with replacement. And so this number is 0.87 based on 2 random samples. That is a very high probability. A high probability really that this light node that accepts the header will do so even in the presence of some hidden information. So now the natural question that arose in the past, well, can some type of coding improve this probability of failure? In fact, since we know the location of something being hidden, a natural choice is therefore to see how well an erasure coding can do. So let's see. So now instead of creating a block that has those 16 chunks, how about we convert that block first into an MDS code word? So you can think of, let's say, Reed-Solomon type code. So now we have 16 original chunks. We add 16 more parity chunks so that the overall chunk length is 32. And still, adversary is going to hide some piece. That is its goal. So it is going to send something to the honest full node with a piece missing. And if everything is fine, if there's nothing missing, honest full nodes can therefore decode coded block, and they can verify the transactions. And if something went wrong during coding, if, for example, these parity check equations were inconsistent because adversary made them so, if there aren't too many of them, then it can, honest full node can realize that something went wrong, and it can send the fraud proof. So what really the adversary wants to do is he doesn't want to be revealed. So he wants to prevent honest full nodes from sending fraud proof in the presence of hidden information. So it must prevent honest full nodes from decoding back this original block. So what it means really, it needs to make it harder for the honest nodes to be able to decode. And if you have a coded system, that means it needs to hide even more coded chunks. So if you have a 3216 MDS code, now the adversary has to hide at least 17 chunks, because that would exceed the erasure correcting capability of the honest node. So now this becomes easier for light nodes to catch these missing chunks using random sampling, because more information needs to be hidden. Now we are headed into the right direction of the probability of improving the probability of failure. So in this case, light nodes can, as we said, they request for samples of the coded block. And again, to remind you, when we have no coding situation, we have 16 chunks. Let's say 2 random chunks are requested, and we already did this derivation. We have a probability of 87% of not hitting this one hidden chunk. But with erasure coding, we can do better. So with the probability of failure, again, using 2 random samples, that goes down quite a bit. And this is already in the territory that is conceived as acceptable. Because by virtue of adversary having to hide more and more, then light node is more and more likely to request the hidden piece, which then adversary either needs to reveal or says, I don't have it, in which case the adversary can be flagged as being such. So far, so good. But in fact, the choice of code matters. So one other issue is, which we briefly touched upon, is the incorrect coding attack. So adversary can also send incorrectly coded blocks to full nodes and can do that by incorrectly generated parity chunks, which are those marked in red here. And honest full nodes can detect and send incorrect coding proof, provided, of course, there aren't too many of these either. And what this incorrect coding proof is really how many computations does a node need to do in order to figure out that something went wrong, or to conclude that nothing went wrong. And the complexity of those computations has to do with the sparsity of the parity check equations. So MDS codes are fully dense in terms of their parity check equations. So the proof size, which is really this decoding here, is proportional to the block size. And that takes time, as these computations take time. So there is the issue of decoding complexity. Another issue is that of the undecodable ratio, which we will refer as to delta. So if you just simplify that sampling probability in going from sampling with replacement to sampling with replacement, just to make it slightly simpler, mathematically speaking, we can introduce the notation and say, well, what is the probability that light node fails based on S random samples? Well, that can be approximated as 1 minus delta to the power of S. And so as a result, so we have seen that MDS codes provide protection and reduce the probability of failure relative to the uncoded case, but they do have burdensome computations. And so let's see if there is another solution that can remedy some of the issues with the MDS codes. So a code to consider that is natural in this regard would be an Ldpc code, because it is characterized by a sparse parity check matrix. And just to quickly remind you, an Ldpc code can be represented by a tenor graph, which is a bipartite representation of a code. Here, circles denote variable nodes and squares denote check nodes. And each check node represents one parity check equation, and they're sparse. So that's good. In fact, previous work demonstrated that Ldpc code, for precisely these reasons, is suitable for this application. And because it has, just in the parlance of blockchain systems, it has a small incorrect coding proof size, precisely because they, in relative terms, they have small check node degree. And we are equipped with linear decoding using, for example, known techniques such as peeling decoder to overcome erasure errors. And so the question is, well, how well can this do? What is the undecodable ratio? What is that delta? The problem with Ldpc codes that actually is quite critical in this application is something known as a stopping set. And what is in particular problematic are small stopping sets. So stopping sets are configurations that exist in the tenor graph representation of the code. So one example is here on the right. So it is a configuration where we see, for example, we have 3 variable nodes. We have 4 check nodes, and every check node is connected twice in this picture, and every variable node is connected at least twice in this picture. So what happens is that if precisely these 3 variable nodes are hidden, if they form that hidden component, then the honest full node cannot decode this, because this is where the decoding stops if you're using peeling decoder. And in fact, if Adversary is clever and precisely hides this particular stopping set, it will prevent honest full node from decoding the block. And so honest full node cannot produce the no coding proof, and we cannot provide any further guarantees in terms of the availability of this block. So what is the probability in this case? Just as an example, suppose we have these 3 pieces here constitute this small stopping set of size 3. Just in this example, this probability now all of a sudden jumps back to over 80% because of the presence of this small stopping set that the adversary was able to take the advantage of. So our contribution is to co-design specialized Ldpc codes along with a coupled sampling strategies to improve on this probability of failure. So we want to build on all the positive attributes of Ldpc codes in this application domain, but also try to improve on it so that we can rectify some of the issues that have come along the way. So what are the adversary models that one can consider? We first considered an adversary that randomly hides a stopping set of a particular size, and we have developed co-design techniques for such adversaries, which I will describe. We refer to them as weak adversary. We also will present co-design techniques for stronger adversaries, where we have 2 versions. We have a medium adversary that is capable of finding all stopping sets up until certain size mu, and it will in fact hide the one that has the highest probability of failure. Strong adversary builds on it, and it can find all stopping set and will select the one that is most difficult, the one that has the highest probability of failure.
Lara, I have a quick question.
Yeah.
So I see we have 2 minutes till
Do you make
then,
any computational assumptions on the adversary, or is it?
Yes. So this is exactly how adversaries, let me go back a slide. So this is exactly how we are separating them. So in terms of computational abilities of the adversary, weak adversary is the one that can find one stopping set. It needs to be able to do something. And then a medium adversary can do more, and then strong adversary can do even more. So this really can be mapped to a continuum of computational resources that adversaries may have, ranging from from limited computational resources to even nodes that are colluding and have, in principle, unlimited resources.
Okay, so this is not like side information that they're magically given. They have to go and do the work to find these stopping sets, and they're right. Okay.
Yes. Okay. All right, so let's discuss the first case, which is the case of the weak adversaries. So the goal is to do the co-design of the Ldpc code and the sampling strategy. So we have a first theoretical result that of all stopping sets of size mu, when a weak adversary randomly hides one of them, so that's a weak adversary, and a light node will sample variable nodes in a given set L, then the probability of failure will be 1 minus the fraction of stopping sets of size mu that it's touched by this set L. And so what is then the idea? If we select a set of variable nodes which touches a large number of stopping sets, we can then decrease the probability of failure. So that is the sampling part. Now, how can we make it better? How can we make it easier to sample a large number of stopping sets at once? So this is where the co-design idea comes in. We concentrate stopping sets to a small section of variable nodes. So the stripe on the top is just a visualization of a code word. So you have systematic nodes and then the coding part. And then these red rectangles represent stopping sets. And we would like that to be as concentrated as possible so that even if we were to just sample the small subset of size 3, we can touch many of them. So make it harder for the adversary to hide these stopping sets. And in fact, what we would like to have, we would like to have the stopping set distribution be concentrated on a subset of variable nodes, because then that gives a leg up to our node that performs sampling. And as I said, then these light node can then greedily sample just this small subsection of subset of variable nodes. Then this becomes a coding question. How do we concentrate stopping sets? As it turns out, the stopping sets in related work that deals with other types of applications has been studied in a lot in the last 2 decades. And there's many results available on this. And we are going to leverage some of these results in this work as well. So when there are no degree 1 variable nodes, stopping sets are either cycles or connections of cycles. And so in order to, instead of concentrating stopping sets, which could look a bit more complicated as these pictures show, we are going to instead concentrate cycles, which are more tractable. And we hope that by concentrating cycles, we will also concentrate these stopping sets. How do we then design codes with concentrated cycles? So that becomes now a co-design problem. So we just started, when we started looking at this problem, we said, well, what are some standard techniques in building practical codes that are cognizant of the cycle properties? So one well-known technique is what is known as a progressive edge growth algorithm. So we are going to actually modify that algorithm. So in the PEG algorithm, we construct a tenor graph in an edge-by-edge manner. So you can think of rooting this tree at some variable node, let's say Vj, and then growing the tree around that node Vj in a breadth-first search fashion, and adding check nodes, which are squares, and then on the next layer of variable nodes, circles, then check nodes, then circles, and so forth. And of course, in the finite length design, we will inevitably at some point hit a cycle. And so how do we add nodes? If we expand it in a following way, if there exists a check node that is not already connected, and it should be connected, and it is a candidate, we connect the one that has the smallest degree. So as the one that has fewest edges so far. And if there is no choice but to repeat a variable check node, we pick the one that is furthest away from this root node, and that will maximize these cycles. So we will select the one with the smallest degree. This, again, as I said, in the finite length design, creates new cycles, and that in a way is inevitable. But what this procedure does, it gives us an option of deferring that unfortunate circumstance for as long as possible. So what we do in this application, because we need a different code that needs to have different cycle spectrum properties, is we are going to modify the part in green in this algorithm to make it so that we concentrate the cycles. And so for that, we use a simple measure of concentration, just entropy. And as you know, uniform distributions have high entropy and concentrated distributions have low entropy. And since we want cycle distributions to be concentrated, we are going to select check nodes such that the entropy of the cycle distribution is minimized. So now we have what we refer to as the entropy constraint, or EC for short, PEG algorithm. And so the part that we modified, it's just one line of code, really. We select check node that results in the smallest entropy of the resultant cycle distribution, and then we update the cycle distribution. So our ECPG algorithm works as follows. So we simply keep the tally, the record of the cycle involvement for each variable node. So for example, if we introduce check node C10 in this example, we have to, it appears in multiple instances because of the finite length constraints. We would, by addition of this check node, we need to add cycle counts for all the nodes that lie on that cycle path. So it would be the case for nodes here that are marked in red for C10, that are marked in 10 for C10, that are marked, so we would update the cycle counts for the nodes 1, 2, and 6, 1, 2, and 7, 1, 3, and 6 also. That's with respect to addition of C10. We will do the same for C8 and C9. So we have 3 sets of these candidate tuples. And then we just map those counts into the fractions. And then we compute the entropy, and this is the entropy of the combined counts. And then we would, so we evaluate that for all 3 check node candidates, and we pick the one that is the smallest. So this becomes our check node selection procedure, which is the one that results in the smallest entropy associated with these cycle counts. And here alpha 4, alpha 6, and alpha 8 refer to the 4, 6, and 8 refer to these shortest cycles. And so this minimization of the entropy of joint cycle counts will ensure that all cycle distributions are concentrated towards the same set of variable nodes. And then once we know that, this now becomes part of our code design. In our sampling strategy, we then want to greedily sample variable nodes that are a part of a large number of cycles, so we can order them because now this is no longer uniform, so it's a concentrated distribution. So we start with the one that has the highest fraction of cycles that it touches. We move on to the next one and to the next one and so forth until we exhaust our sampling budget. And so here are some representative simulation results. So here the blue lines, the blue solid line represents cycle count, rather the fraction of cycles touched by a variable node in the original PG design. PG, mind you, is a good design, is a good way to make a good, kind of good off-the-shelf Ldpc code. So it already has, sorry, this is the red line. So the red line already has a bit of a non-uniformity by virtue of differing cycles. But what we did, since we modified this co-design procedure, we made it even more so. So that is the solid blue line. So we improved in going from solid red line to solid blue line. We made it more non-uniform. So we are also plotting here cycle distribution for cycles of length 8. They are jagged because we are indexing the x-axis with respect to nodes, they're indexed with respect to cycle 6 fractions, but nonetheless, you can identify the trend that the blue jagged line is really on average steeper than the red jagged line, and that is what we want. So we are able to concentrate both cycle 6 and 8. But what we are really after is stopping sets. And so we are indexing these variable nodes with respect to the fraction of the cycle 6 that they touch. And if we do a line fit through this, you can see again that the blue solid line is steeper than the red solid line. And that is going to be the case for stopping sets of size 11 and 12, which are of interest in this code design. And this is how we can capture more of what matters within this code. And then we can conclude then by concentrating cycles, we have in fact achieved our goal of concentrating stopping sets as well. So here are some simulation results. So we start first with random sampling. This previous result dealt with the Ldpc code construction that is ensemble based. And as a result, because it's an ensemble based, the smallest stopping set is of size 6. Our first improvement really is to use our code construction. This is entropy based with random sampling. And here these are results with respect to different stopping sets that are of interest, 10, 11, and 12, because those are the smallest ones we have. Then we said, well, what if I only, what if I did the original code, but I improved the sampling strategy? Well, then we have an even further improvement, and the best of both worlds comes indeed when we improve both the code and when we improve the sampling strategy that is now cognizant of the way the code has been built. So these, in a nutshell, concentrated Ldpc codes, concentrated with respect to stopping sets, with greedy sampling, improves the probability of failure against a weak adversary. So just briefly, I want to also show you some results for our medium and strong adversary. So here math slightly changes because of the ability, computational abilities of the adversary has changed. And so what we refer to this as LP sampling because the sampling now needs to solve a linear program. So we are looking at the minimizing the worst case of what an adversary can do. So this G is a certain function in X, where X denotes the Xi is the probability of sampling the ith variable node. So this is just a bookkeeping over these individual probabilities. So since they have to be between 0 and 1, and they have to sum up to 1, that's why we have these linear constraints on them. And so the goal is to co-design idea is then to design an Ldpc code such that it produces good sampling strategies, i.e. minimizes the probability of failure when this LP sampling is used. So this is the case for the medium adversary, and we just need to extend this for the strong adversary, where we introduce an additional parameter delta, which is the minimum probability of sampling a variable node. And so this probability of failure for a strong adversary, what really just changes is this function that sits inside of this min-max sampling here. So to deal with the strong adversary, we build on the case of the medium adversary. And so then the Ldpc co-design becomes the following. So we want to design an Ldpc code to reduce this optimal objective of our LP sampling, where L is now the list of all cycles. So we don't deal with stopping sets directly for the same reasons as we didn't deal with them before. So we're going to deal with cycles. So now we change again a few lines of code. And we first actually pre-process this. So we select check nodes that form a smallest number of new cycles that is beneficial for this setup. And then we select the one that will result in the smallest value of this linear program. And then we also made an observation that reducing the number of cycles and slightly altering this set L, so it contains only cycles that have what is known as the low extrinsic message degree, which really refers to the connectivity to other nodes and cycles, which is a proxy for stopping sets, also improves the performance in our LP sampling. And here are some simulation results. So we again start with the ensemble and random sampling where mu is 6, which is the size of the smallest stopping set. The first result is if we just use PG and random sampling. So mu naturally increases by virtue of using a relatively good code. And then we have results both for strong adversary and for the medium adversary. Now first with the original PG construction and our improved sampling and our new code in our choice of sampling. And so again, as we shown also in the weak adversary setting, it is beneficial to both improve the code and the sampling strategy that the light nodes would employ. And just to also briefly mention the incorrect code proofing size, that's something I referred to as before as being one of the deficiencies of the MDS codes. What we see here, this is for various parameters, is because the incorrect coding proof size depends on the maximum check node degree. These numbers are comparable. In some cases, they're even better, but they certainly don't get much worse. So these new constructions do not largely negatively affect the incorrect coding proof size because, again, the degrees are kept at relatively low values. So this concludes the first part of my talk. So what we've seen thus far is a setup in which we have an architecture that has light nodes in it. And light nodes, again, are introduced to alleviate some of the storage burden. But the presence of light nodes opens them, makes them vulnerable to a data availability attack where an adversary can hide a small portion. And we then proposed a coding-based scheme such that this data availability attack can be made more difficult, i.e. that it doesn't occur with too high of a probability. Next one I will talk about is a different type of data availability attack. And now this one will be focused on what happens in the side blockchains. And as we said already, side blockchains are introduced with the purpose of increasing throughput. As recognized also in previous work, side blockchains with the majority of dishonest nodes are vulnerable to data availability attacks. And what happens in this setup? Adversarial side blockchain node, it pushes the hash commitment to the trusted blockchain, but since it's an adversary, it can create an invalid block. And as a result, for block is not available to other side blockchain nodes. And the invalid block, because it's hash being pushed to the trusted blockchain, it does in fact become part of the transaction ordering in the main, this trusted blockchain, and that of course can be problematic. We just quickly mentioned that data availability attack cannot occur when the side blockchains have a majority of honest nodes, because then they can collectively say, well, that something is missing. But because of a situation that we deal with, which is the majority of dishonest nodes, we cannot, in fact, rely on the majority being trustworthy to let us know that something went wrong. So what has been proposed in previous work by others is an alternative architecture. A solution was introduced that uses what is known as a data availability oracle. And we can view this data availability oracle as a gatekeeper that sits between side blockchains and the trusted blockchain. And the goal of the oracle layer is to accept a block produced by a side blockchain, and then to collectively and efficiently store chunks of this transmitted block to guarantee availability of this block. And then it itself will push the hash commitment if it deems that the block is available, and then this hash commitment goes on to the trusted blockchain. Oracle nodes themselves can be malicious, but there is a solution that incentivizes Oracle nodes so that it still does have honest majority. Again, and unsurprisingly, it is a good idea to use coding to alleviate some of the previous issues in terms of data availability. So this transaction block now can be chunked and coded. So now we take L chunks as before, and we convert that to M-coded chunks. And as a first step, we can consider doing that using an MDS code. And now these coded chunks are dispersed amongst the Oracle node using chunk dispersal as marked here on the left. And if you have an MDS code, if at least L coded chunks are present amongst honest Oracle layer nodes, then the block availability is guaranteed, i.e. we have enough to decode correctly. And so an alternative, again, to MDS codes is to use Ldpc codes for the same positive reasons that we had before. We have linear decoding complexity. We have small incorrect coding proof size due to a sparsity in the parity check matrix. And unfortunately, yet again, we have an issue of small stopping sets. And if a variable node corresponding to a small stopping set is, if those variable nodes are hidden, then the original block code cannot be decoded using a peeling decoder. So same issue as before. And previous work said that randomly constructed Ldpc codes can provide a guarantee on the minimum stopping set size with high probability. So in this work, we are going to take on a deterministic viewpoint so that the code is not generated based on a family, but rather using a deterministic procedure. Before I describe that, I just want to show you the dispersal protocol, which is the rule about which Oracle node stores which chunks. And it specifies which specify coded symbols that each Oracle node will receive. And another parameter of interest to us is this MMIN, which is the minimum stopping set size of an Ldpc code of block length M. And by virtue of being able to recover from stopping sets, we say that every gamma fraction of nodes needs to receive at least m minus m plus 1 plus m minus mn plus 1 coded chunks. We also have to deal with the malicious oracle nodes, and we'll denote by beta the fraction of those nodes. And so the result says that if more than gamma plus beta fraction of nodes vote that the block is available, so we now guarantee that we have honest majority with enough information, then the hash commitment is pushed onto the trusted blockchain, and then the oracle can't guarantee block availability. Just as a side note, it is the side blockchain that performs Ldpc encoding and dispersal, just like in the original architecture. The goal here now becomes to minimize communication cost, which is the amount of data that is communicated to oracle nodes during the dispersal step. So dispersal protocol in the previous work says that every gamma fraction of oracle nodes needs to receive at least m minus mn plus 1 coded chunks. And they designed the solution there was to do this randomly, which is sampling with replacement. And of course, the issue here is that if the stopping set size is small, so if min is small, we need to send more and more chunks to oracle nodes, which of course then increases the communication cost. So how can we design Ldpc codes that have large, smallest stopping set size? That is, of course, a known problem in coding, and no known solution exists in general. So instead of tackling this very hard open problem, what we do instead, we are going to design specialized Ldpc codes in a tailored dispersal protocol to significantly lower the communication cost. So a lot of this will have flavor of what we had seen before. So now our dispersal protocol is a two-step protocol, which has two first step, which is the secure phase. In the secure phase, we treat all small stopping sets up to a given size in unified manner. So coded chunks are dispersed in a communication efficient way, such that small stopping set failures simply cannot occur. And in the valid phase, we actually refine the previous protocol for larger stopping sets, such that this is guaranteed with high probability under large stopping set failures. And our focus is then to design codes to reduce the communication cost of this first, i.e. secure phase. So what is of interest here is if you look at the stopping set S, we have the neighborhood set, which is the neighborhood set of S. We'll look at F, which is the maximum number of malicious oracle nodes. We'll say that this stopping set is securely dispersed if the neighborhood of S exceeds the maximum number of oracle nodes, of malicious oracle nodes. So that means there exists at least one honest node that has some piece of this stopping set. And so that is the definition of being securely dispersed. And in this case, we have just enough information that a failure of stopping set cannot occur. Now we are looking at all stopping sets of a particular size up to, let's say, mu, and we want to securely disperse all of them. And so that there will be no block unavailability in those small stopping sets. So how to do that efficiently? Because now we have many stopping sets. In fact, we're going to have hundreds, if not thousands of them. So for that, we introduce the set of variable nodes that cover all stopping sets in this set S. And what we want to do is find the minimal such set. So a picture on the left shows a collection of stopping sets and color-coded variable nodes that are in this stopping set. And now we want to isolate the smallest possible collection of variable nodes, such that in this collection, we have variable nodes in a way that if for each stopping set, there exists at least one element in this set V. So these two, for example, have blue, then this one has red, and this one has yellow, and so forth. And that is a small set. So we want to cover a lot of stopping set with a small set of variable nodes. And those are the ones that are going to be dispersed to our F+1 variable nodes, and that will guarantee simultaneously secure dispersal of all small stopping sets. And in the valid phase, we do, as I said, a refinement of the previous method where we do a slightly different type of sampling. So we say each Oracle node receives coded chunks that correspond to uniformly chosen k-element subset of all the k-element subsets of m-coded chunks. And we then propose an upper bound, which is a combinatorial result, to upper bound the probability that this dispersal is not possible. And we then find k star such that this upper bound is below a threshold in probability, which can be set to a particular value as a system parameter. And that's how many we then disperse. That's the k star here. And that shows an improvement over the previous method, and that will guarantee availability with probability of at least 1 minus p threshold. So the overall, just to summarize, we have two stages, which is the secure stage, secure phase. No small stopping sets can be hidden, and in the valid phase, we guarantee availability of with high probability of large stopping sets. For the first step, we deeply care about these variable nodes in the set V, and the communication cost is now proportional to the size of the set V times how many nodes F we have. And so we want to design a code that has a small set of these variable nodes that will cover as many of the stopping sets as possible. Again, we're going to do that by modifying the PEG algorithm. So again, I'm showing you the same picture from before, but now our check node selection criteria has changed. So now we want to select the one that results in the smallest greedy set, the smallest cardinality of this greedy set of variable nodes. And again, we can utilize additional properties of cycles vis-a-vis their connectivity to other cycles along the ways of what we did before. And let me now show you some results. Here we have n equals to 9,000. This is the number of Oracle nodes. Beta 0.49 is a fraction of malicious Oracle nodes. M is the size of the code. Block size is 1 megabyte, and threshold, that parameter that we use in our protocol, is set to the 10 to the minus 8. Code rate is 1/2, and the best we can do in terms of gamma is 1 minus 2 beta. And so what this table shows is we are now looking at these first this set V that covers as many stopping sets as possible. So our construction shows a bit of an improvement over the PG, but that does indeed help. CS refers to cost of the secure phase, CV is the cost of the valid phase, and CT is the total communication cost. Smallest set size here for the PG algorithm is 17, so we will use that as the baseline for our two-step dispersal protocol. So just in terms of plotting the communication cost, so the goal is to reduce that communication cost. So that top line in red, I'm going to mark it here as a red dot. And then if we do our secure dispersal with the cutoff being set at stopping set size of 20, we reduce that even further. So the reduction is right to left in terms of the overall cost. So we now go from 5 point something to 0.42. And then we go down to our secure dispersal along with our code design. And then this gets even closer to the best one could do, which would be designing a code that has a large stopping set size, which is still an open problem. So let me now show the last set of simulation results. So this is the red line is the original PGA algorithm with the baseline dispersal along the lines of what was done in the previous work. The next line is the original PG with our secure dispersal protocol. And the next one is our code with our dispersal protocol, and it gets closer to this lower bound. The plot on the right shows so the plot on the left shows improvement, rather the reduction in the total communication cost as we change the number of Oracle nodes. And the plot on the right shows how these numbers change. How does the communication cost change as a function of adversarial oracle nodes, which is that parameter beta. So we stop just short of 0.5. And we have a reduction, as you can see, plots are monotonic and uniform. We have a reduction in the communication cost, both in terms of the different number of oracle nodes as well as the adversary fractions. So I'm almost out of time, so I'm just going to go to conclusion. So the key takeaway from this presentation is that there's a lot of different alternatives to the baseline blockchain architectures that have been now proposed and actively investigated. And there is a role for a coding type solutions that they can play in these systems for a variety of reasons. But what we have also recognized is that off-the-shelf LDPC codes, despite their many positive properties, that are previously optimized for other applications like AVGN channel, BSC channels, may not be optimal for the type of errors, or rather type of attacks that we see in blockchain systems. And this has in fact necessitated a new look on LDPC codes and how one would go about designing them. So they need to be tailor-made with a different type of design criteria that is better suited for these applications. So just looking beyond LDPC codes, we are now actively investigating the use of other types of coding constructions, namely polar codes, and see how well they could do in these types of systems. And this concludes my presentation, and these are my references that refers to prior work and the papers that we have submitted and published, and I'll just leave it at this conclusion side here. Thank you.
Thank you, Lara. Any questions?
I guess because I'm not familiar with blockchain, anything like, except for what you sort of read on the internet. I guess, if you do, you've designed these new codes, I guess, what's the path? Like, I have a better sense of, like, you design a new code for wireless, like, how does it end up into getting used? How does it, like, how would something like this end up getting, like, what's the path to actually it becoming deployed? Would it be a new cryptocurrency or something like that, or like?
But it can improve your original system. So we are trying to overcome some of the issues that arise with scalability. For example, not being able to involve a lightweight nodes. And if you are in fact able to involve lightweight nodes, well, what does it mean in terms of other problems? Like, and then data availability problem naturally just arose. And so this work on introducing codes is very recent. It's not something that has been deployed, but this is sort of the onset of these types of results. But the introduction of light nodes, parallel blockchains, that's something that people have considered already.
Oh, okay. All right. Because there's a large ecosystem that you're building on here. So.
Right. But it also depends on the application. You want if you want to include as many players as you want, inevitably these issues will arise.
Yeah, that's right. Any other questions? So how popular are blockchains at the moment? I know there were some in the beginning of the year. I think that were cryptocurrency popularity changed because of, I don't know, Elon Musk saying something, or are there any recent developments like that?
So I can comment on a few things. So I know some of these blockchain systems are actually used at MIT for record-keeping purposes. So I don't know if you can say that MIT is the forefront of these technologies, but they want to try. So their diploma record-keeping system or transcript-keeping system is based on the blockchain technology. So something along the lines of what we have discussed here. And of course, it's something that is in the news is, the monetary value associated with blockchains. I just got an alert, coincidentally, during this presentation from my stock market app that, Bitcoin is now over $60,000. So I don't know, I guess I can have regret of not buying it on time. Yeah, but.
There was a falafel place in Jersey City that said that they said they would take Bitcoin. And I remember in 2015 or something, I was, it's like, oh, who'd pay in Bitcoin? But anybody who did, they made a lot of money off of that.
Right. So this is something new. Of course, we don't understand everything about it yet. maybe some new applications will emerge, not necessarily just for finance, but just for general processing. This is a completely decentralized system. So the way I would see this is maybe some lessons learned in these types of systems could also carry over to some other distributed applications.
So there is also an issue, I think, with the delay in the blockchain systems. Do codes slow down or speed up these systems?
Yes. So that's a great question. So one of the reasons why these side blockchains are introduced is to mitigate some of these issues with the delay in throughput, really. So it takes time for the confirmation. So what I did not discuss at all in this talk, and this is one really sort of the core thing of the blockchains, is this security aspect of it. So what really gets transmitted at this is not this raw block or this coded chunk. What really gets transmitted is what is known as the Merkle proof associated that gets built based on the Merkle tree of this coded piece, and that is a cryptographic, I guess, guarantee of the availability of this, in cryptographic terms, availability of this block. So coding does not necessarily slow that down. What the coding does is enables, so what is primary here is the sort of opportunity to explore a completely different type of architecture, whether by involvement of light nodes or parallel blockchains, but they don't come for free. And so these new issues arise, and we are trying to, we want to attempt to resolve some of these issues using, let's say, a coding theoretic perspective. And some of that benefit might be lost because, of course, as you said, coding will take some time, but at the same time, the price paid, it seems to be favorable towards coding, given that it can still solve a problem, which is the data availability problem, which is a big problem to address.
Exactly. Thank you very much. I actually have one more question, but let's ask other people. Any questions?
So I have a comment.
Yes.
So I have actually, I don't know what the financial systems are using, but they might be using something that maybe not so unrelated to this. I don't know if you've been following. There's quite a bit of discussion on the topic that there are big cases where people kind of like see the transactions go through, but actually it doesn't go through, and people will be losing money. And I've heard this thing happening outside the country even more. So this,
So yeah, there's of course issues with, blockchain is not a bulletproof system. It was proposed because it offers this anonymity in decentralization, but of course it can be abused. So there is other issues associated with blockchain, which is that proof of work, proof of stake, that these all come in, what an adversary can do, which is something we did not discuss today. It can fork off and start building its own chain, and then force everybody to follow that. So there's other ways in which things can go awry. This is not certainly the only way, but this is one way where techniques that we collectively might be familiar with could help remediate. There are other ways in which a blockchain system can fail, yes.
Okay, thank you.
So I have a non-technical question. Where do you think this type of work being done? Where do you see that? Like, would that be electrical engineering department or computer science or math? I ask this question almost every person who comes and gives us a coding talk, because we have fewer and fewer students who keep up with it.
That's a great question. This is something that was really of interest to my own students who are ECE students. They wanted to tackle this problem, and I supported them in that. And they are ECE students. So I don't know, that's just one data sample, so I can't really say. I mean, of course, a problem like this can certainly have a home, rightfully so, in EC, in CS, in EE, in math. So I don't know, frankly.
Yeah. No, thank you for trying to answer this question. We just have been wondering here in designing our own curriculum what.
So I teach a course in our master's online program, also that is like applications of coding in a variety of different systems, and this is something I touched upon. And this program is for people who are in industry. So this was online program from day one, even pre-pandemic. And so these people the students would take one course per quarter along with their full-time job and then get a degree, let's say in 2 years. And even though they're engineers, most of them are engineers, they work in companies like Broadcom and Qualcomm and things like that, Northrop Grumman. They care to know about these things, actually. They find this interesting.
That's exactly why I asked, because in industry, sometimes our students who come from industry, they take coding theory, but while they're...
Exactly the feedback I got.
Because you cannot be without that. Yeah.
They would say, oh my God, there is all this math that we don't need to go into great details about primitive polynomials, and all this fancy abstract algebra, but just enough for them to understand how, let's say, Reed-Solomon code works or how an erasure coding works. That for them is already a big win, because now they can map that to whatever it is that they're doing it in their jobs. And I always get disproportionately positive feedback on that class versus maybe something one would consider more basic. So they always enjoy this class. So no matter what. And these are people who are in industry full-time.
Exactly. That's exactly actually why I asked, because it's undoubtedly a very important topic, that coding is the best way we can deal with uncertainty. So it's going to be important, even more and more important, because we will be building things from unreliable components, having more cyber attacks, etc.
It's like a fundamental skill, like programming is a fundamental skill. Knowing some math in this domain, I feel it's a fundamental skill. Personal opinion, and of course I'm super biased, so.
Yeah, well, thank you very much. I on purpose recorded also this Q&A, because I think it's an important discussion for students to hear if they look.